Hello, my name is Matt Altis, and this is my presentation for A 2610 Lab 4, where we will be understanding pulse combustion using a Rijke tube. To introduce the concept of pulse combustion, I will be using the figure on the right of a pulse jet. So in these systems, you have combustion intensity fluctuating with time, and this is due to three different properties. You have heat release, as well as pressure and velocity oscillations, which occur throughout the length of the system. Now, these kind of engines have their advantages. For one, you can increase the combustion intensity due to more efficient mixing of fuel and air. You can also generate a pressurized output without the need of external mechanical devices. However, due to the oscillation and system driving to resonance, these jet engines can be potentially dangerous. For our experimental setup, we used a Rijke tube as our pulse combustor. So this tube is located in the Engineering, Science, and Mechanics building in Lab G2. It is 6 feet long and it extends outside of the lab. It consists of a burner that is fueled by propane here at the bottom. Additionally, to take measurements, there are 3 of these pressure transducers that are each 18 inches apart. So what these transducers do is take a physical measurement, in this case pressure, and it converts it to an output current, which can be then converted to an RMS voltage by an oscilloscope. Additionally, this device here is a photomultiplier that optically records the reaction rate. That's why we have it sitting right next to the window where the burner is. For our experiment, we ran the burner at 3 different heights, and our goal was to achieve resonance in the tube, or where it was making a loud humming sound. So starting out at 0 inches of displacement, we ran tests with both the valve closed and open. With the valve closed, we drove the system to resonance to where the tube was making a noise and increased the height to 2 inches. We let the burner continue there for a while before increasing the height until resonance stopped. And we found that the tube stopped making a noise when we had a displacement of 5.5 inches relative to the starting position. We recorded RMS voltage for each of the 3 transducers, as well as the frequency and amplitude of the photomultiplier. Finally, we measured the associated phase angles of the transducers and photomultiplier. For our data analysis, we first converted our pressure signals from the transducers to sound pressure level in decibels. So if you'll recall, we took measurements in voltage for each of the transducers. So we converted that first to millivolts, and then using a calibration curve of 96.8 millivolts to psi, we obtained our pressure signals in psi. Then to get from psi to decibels, we use the following logarithmic formula, where we have our measured PRMS divided by our PRMS threshold, which was given as 2.9 times 10 to the negative 9 psi. Another important measurement was our estimation of the tube's resonance frequency, where we have our frequency as square root of gamma RT, which is the speed of sound of air at our conditions, over 2 times the length of the tube, and we estimated about 94 Hertz for our resonance frequency. Finally, we converted our associated phase angles to relative phase angles with respect to the middle transducer, and we did that by subtracting each associated phase by the phase at the middle transducer. Our first set of results consists of our measurements at 0 inches of displacement with both the valve open and closed. So, as we said, when the valve was closed, that was when the tube began to resonate or make the loud humming noise, and that is representative of the peak frequencies, which are significantly higher than when the valve was open. We can also see a relatively larger amplitude compared to the open tube when the tube is closed. As we continued to increase the height of the burner, we see at 2 inches resonance is still occurring, and that makes sense because our frequency is still 100 Hertz, very close to our estimated value for resonance frequency, and our amplitude is still around 150 decibels, which is not much different than what we measured at the 0-inch position with the tube closed. Finally, when we increase the height to 5.5 inches, resonance stops, and this can be represented by a decrease in the peak frequency back down to 10 Hertz, as well as a decrease in the amplitude. From our data results, there are a few key findings that we noticed. First is that resonance depends on both our burner height and the valve position. So if you'll recall, when the valve was open, the system could not be driven to resonance as pressure is able to escape from the tube. Another finding is that the output amplitude was higher when the tube was at resonance. And finally, we were able to confirm our estimated resonance frequency as our peak value was very similar to our estimated resonance frequency value for our tube.